Welcome, my friends! You probably already know that if you have the same constant on the top and bottom of a fraction, that it can be cancelled. For example, 2x over 2, of course, simplifies to x. This also applies to variables. So take, for example, 8xy divided by 14xyz. We have both x and y on the numerator and denominator, so they get cancelled in the simplification. 8 over 14 can be reduced to 4 out of 7, so our final simplified form is 4 divided by 7z. Now, if you have powers that differ from 1, it turns out that you can subtract the exponents to simplify your expression. For example, x to the fourth power divided by x squared is the same thing as x to the 4 minus 2 power, or just x squared. The reason this works is because an exponent in the denominator can be written in the numerator with a negative exponent. Take the same example, x to the fourth over x squared, which could be written as x to the fourth times x to the negative second power, as we can move the x squared from the denominator to the numerator as x to the negative second power. We know that this simplifies to x squared by the product rule. This is the same result we would get from taking 4 and subtracting 2. Consider that x to the third power divided by x to the fifth power is the same thing as x to the 3 minus 5 power, which equals x to the negative second power. Usually we write expressions without negative exponents in their most simplified form, and we know that x to the negative second power is the same as 1 divided by x squared. A shortcut is to take whichever exponent is larger, the one in the numerator or denominator, and subtract the smaller exponent. The result will be a positive exponent, which should go in the same location as the larger exponent. For example, the same problem, x to the third power divided by x to the fifth power, could be simplified by noticing that the larger exponent is in the denominator. So our answer also goes in the denominator as 1 divided by x to the 5 minus 3 power, which is just 1 over x squared. In general, this simplification process is called the quotient rule for exponents. We could also have a constant along with our exponents, such as in 32y to the 7th power divided by 28y to the 3rd power. Both 32 and 28 are divisible by 4. 32 divided by 4 is 8, and 28 divided by 4 is 7. We can subtract the exponents on the y terms to get the expression 8y to the 7 minus 3 power divided by 7. Simplifying, we have 8y to the 4th power divided by 7. Now, if one or both of the exponents are negative, you should change them to positive exponents first before simplifying. For example, take p to the 8th power divided by p to the negative 7th power. We can rewrite this as p to the 8th power times p to the 7th power by moving the p term up to the numerator and making the exponent positive. This simplifies to p to the 15th power by adding the exponents. If both exponents are negative, such as in x to the negative 3rd power divided by x to the negative 6th power, both the numerator and denominator will need to change before we simplify. This problem can be rewritten as x to the 6th power divided by x to the 3rd power. We can then simplify by subtracting the exponents to get x to the 3rd power. Let's consider some problems applied to multiple variables. Consider a to the 6th power times b to the 3rd power divided by a to the 6th power times b to the 4th power. Let's consider the terms one at a time. For the a terms, we have a to the 6 minus 6 power, which is equal to a to the 0 power, which we know to be 1. For the b terms, the higher exponent is in the denominator, so our answer will be 1 divided by b to the 4 minus 3 power, or just 1 over b. Putting everything together, we have 1 times 1 over b, which is just the same thing as 1 over b. If you don't like that explanation, you can think of this as b to the 3 minus 4 power by subtracting the exponents, since they are divided, which gives you b to the negative 1 power, which is the same thing as 1 over b. Let's try one with negative exponents. We have a to the 6th power times b to the 4th power times c to the negative 9th power divided by a to the negative 2nd power times b to the 8th power times c squared. First, let's switch any negative exponents from the numerator to the denominator, or vice versa, and then rewrite them as positive exponents. Let's consider one letter at a time. A to the sixth stays the same in the numerator, since it's already a positive exponent. A to the negative second power can be brought up to the numerator as a to the second power. Our b terms don't need to change, as they're both already positive. C to the negative ninth can be brought down to the denominator as c to the positive ninth power, along with our c squared. Now we can simplify. A to the sixth times a squared is equal to a to the eighth power. For the b's, we can subtract the powers, 8 minus 4, to get 4, which can be written on the denominator, as that is where the higher power was. C squared times c to the ninth power is c to the 11th by adding the exponents. Our final answer is a to the 8th power divided by b to the 4th power times c to the 11th power. Let's try this one. 8x to the 4th power times y to the 5th power divided by 36x to the 5th power times y to the 3rd power. Our constants are both divisible by 4. 8 divided by 4 is 2, and 36 divided by 4 is 9. So we have 2 ninths in our fraction. Our x terms simplify to 1 over x, as the higher x term is in the denominator. Our y terms simplify to y squared by subtracting the y exponents. Putting everything together, we have 2y squared divided by 9x. We can combine the quotient rule with the power rule in a problem like this. 3a to the 5th power divided by 2a to the 7th power times b to the 3rd power, all to the 3rd power. We can simplify the inside of the parentheses first to make the problem a bit easier. The constant terms can't be reduced, but the a term can be reduced to a squared in the denominator, as 7 minus 5 is 2. b to the 3rd power doesn't change, so our new expression is 3 over 2a squared b to the 3rd, all to the 3rd power. Now we can apply the exponent to each component of our problem. We have 3 to the 3rd power divided by 2 to the 3rd power times a squared to the 3rd power times b to the 3rd power to the 3rd power. Simplifying everything, we have 27 divided by 8a to the 6th power b to the 9th power. 27 over 8 can't be reduced, so this is our final answer. Now, sometimes you might have a fraction raised to a power, except that power is negative. For example, consider 2/3 to the negative second power. This is the same thing as 2 to the negative second power divided by 3 to the negative second power. But we know negative exponents can be rewritten as positive exponents if we move them from the denominator to the numerator, or the other way around. So 2 to the negative second power divided by 3 to the negative second power can be rewritten as 3 squared over 2 squared, which is the same thing as 9 over 4. The shortcut is, you can change the exponent on a fraction from negative to positive by switching the numerator and denominator of the fraction, which is called the reciprocal. To see another example, consider 5/8 to the negative second power. This is the same thing as 8 over 5 squared, which is equal to 64 over 25, which cannot be reduced. This can be applied to more complicated expressions. Consider 3m to the 3rd power divided by 4m to the 6th power, all to the negative second power. You could apply the negative second power to each component of the expression, but that will cause more work later, as you'll need to switch everything around to get rid of the negative exponents. Instead, let's rewrite the problem as the reciprocal without the negative exponent. We have 4m to the 6th power divided by 3m to the 3rd power, all squared. Now we can distribute the square to each term. We have 4 squared times m to the 6th power squared over 3 squared times m to the 3rd power squared. 4 squared simplifies to 16. M to the 6th power squared simplifies to m to the 12th power. 3 squared simplifies to 9, and m to the 3rd power squared simplifies to m to the 6th power. We can subtract our powers on m to get 16m to the 6th power divided by 9, which is our final simplified expression. Let's try this one. X to the 5th power times y to the 6th power, all to the negative 3rd power, divided by 4x to the negative 5th power times y to the 6th power, all squared. Let's apply our exponents to each of the components of our problem. We have x to the 5th power to the negative 3rd power times y to the 6th power to the negative 3rd power divided by 4 squared times x to the negative 5th power squared times y to the 6th power squared. Simplifying the numerator, we have x to the negative 15th times y to the negative 18th. And on the denominator, we have 16x to the negative 10th power times y to the 12th power. Now let's rewrite this without negative exponents. The x's switch so that we have x to the 10th power on the numerator and x to the 15th power on the denominator. We have y to the 12th power times y to the 18th power on the denominator as well. Of course, we still also have our 16. Subtracting the exponents on x, we have x to the 5th power on the denominator, since the denominator power was larger, and we have y to the 30th power on the denominator, as well as our 16. There is nothing left on the numerator, so we just have 1, which completes the simplification of this expression. Okay, one final problem. We have 3x u to the 3rd power divided by z to the negative 1st power, all to the negative 2nd power, times u to the negative 2nd power times z to the 5th power. I'm going to deal with what we have in the first set of parentheses first by rewriting it as the reciprocal and with a positive exponent. So we have z to the negative 1st power divided by 3x u to the 3rd power, all squared, times u to the negative 2nd power times z to the 5th power. Now, applying the square to everything, we have z to the negative 1st power squared divided by 3 squared times x squared times u to the 3rd power squared, all times u to the negative 2nd power times z to the 5th power. Simplifying, we have z to the negative 2nd power on the numerator and 9x squared u to the 6th power on the denominator. We can rewrite this all as one fraction. Z to the negative 2nd power times u to the negative 2nd power times z to the 5th power divided by 9x squared u to the 6th. Simplifying the z terms, we have z to the 3rd, as negative 2 plus 5 is 3. We can rewrite u to the negative 2nd as u squared in the denominator, so that we have z to the 3rd power divided by 9x squared u to the 6th u to the 2nd, which simplifies to z to the 3rd power divided by 9x squared u to the 8th, when we add the u exponents, which is our final answer. Okay, that completes the example portion of this video. I'd like to just quickly summarize all the properties of exponents we have discussed in this video, and in the previous video. The product rule states that if two terms with the same base are multiplied, their powers can be added. The power rule states that if an exponent is raised to a power, the exponent and the power can be multiplied. The zero exponent property states that any non-zero value raised to the zero power is equal to 1. The power of a product rule allows us to distribute that power to each term that is being multiplied together. For negative exponents, we can bring them from the numerator to the denominator or vice versa. Now, all of those were the properties that were discussed in the previous video. In this video, we discussed the quotient rule, which allowed us to subtract exponents from the quotient of variables with the same base. We discussed the power of a quotient, and how the power could be applied to both the numerator and denominator individually. And finally, we discussed negative exponents with a quotient, and how we could rewrite the expression as the reciprocal with a positive exponent. Alright, my friends, that completes our discussion of exponents.